Now, it turns out that we can also determine the surface temperature of the star. Can be determined from its spectrum using so-called Wien's law, or sometimes it's also described as the law of black body radiation for the reasons that I won't explain. Okay, let me explain what the Wien's law is and how it's being used. As I pointed out before, any body of given surface temperature emits the electromagnetic waves of all possible wavelengths, right? Where it emits most of the energy depends on at which wavelength, I should say, it emits most of the energy. It depends on the surface temperature. So what you have here on the horizontal scale, which you can see well, on the horizontal scale you have wavelength in nanometers, and here what is plotted is energy emitted at a given wavelength. And the Wien's law tells you basically, if I denote the wavelength where most of the energy is emitted with lambda max, that the lambda max in nanometers is related to the surface temperature in degrees Kelvin as follows. You have 3 million, and then here temperature in degrees Kelvin. Now the Kelvin scale is so-called absolute temperature scale, and it turns out that 0 degrees Kelvin is the lowest temperature that can be achieved in nature, and it corresponds to minus 273.16 degrees centigrade. So I'll write it down what the relationship is. So you can see that the higher the surface temperature, I'm dividing by bigger number, the wavelength at which it emits most of energy moves to the shorter wavelengths, right? So lambda max decreases with increasing temperature. So what astronomers do, they take the light from a star, then they resolve it using a prism into all possible wavelengths, and they can also measure how much energy is carried by each wavelength, and in this way they can obtain this distribution of energy per wavelength. Once you have this shape, then it can easily, you can easily determine the wavelength at which you get most of the energy, and then you use this relation here, or its inverse. I can solve this for T to find out the surface temperature. Okay, that's one way how we can find out the surface temperature of a star. Let me just illustrate this with another overhead. Okay, so how the lambda max, the wavelength at which most of the energy is emitted, depends on temperature, is illustrated with these three graphs. Here we have a cool star, and it turns out that the temperature relates to the color as well. Why? Because here we get the maximum in energy at a wavelength of about 1,000 nanometers. That corresponds to the red part of the spectrum, slightly beyond, longer than 700 nanometers, right? So cool stars appear to be red. Then if we go to a star that has twice the surface temperature, using the Wien's law, the wavelength at which it emits most of the energy is halved, so it's about 500 nanometers, corresponding to the yellow light, and that would be our sun. And then if I go to a star whose temperature is, surface temperature is twice as large, 12,000 K, then the wavelength at which it emits most of the energy is half of this one here. That is, it is going to be 250 nanometers. And that's actually already in UV part of the spectrum. Or if it was slightly longer, it would appear to be blue. So cool stars appear to be reddish. Very hot stars appear to be bluish. And the reason is that the wavelength at which a star emits most of the energy is inversely proportional to its surface temperature. The cooler the star, the higher the wavelength at which it emits most of the energy, and therefore its color is going to be on the red side, and vice versa for a blue star. Wien's law, or the law of blackbody radiation, refers to this curve where here we have the wavelength and here energy, and it has this kind of shape, and most energy is emitted at a particular wavelength that I'll call lambda max. So the Wien's law says that that wavelength at which most of the energy is emitted is given by a factor, numerical factor of 3 million over the temperature, but this relation is valid when you express lambda in nanometers and temperature in kelvins. Okay, so the way to relate the temperature in kelvins to the temperature in degrees centigrade, you have to add to the number giving the temperature in centigrades 273.16. So that when the temperature in centigrades is minus 273.16, the same temperature expressed on the Kelvin scale is 0. The point at which water freezes at normal atmospheric pressure of 1 atmosphere is 0 degrees. On Kelvin scale, that temperature would be 273.16 degrees Kelvin. This same relation can be turned around, and I can write that the surface temperature is then 3 times 1 million over the wavelength at which most of the energy is being emitted. So as I explained, you take the starlight, you resolve it in the spectrum in all possible wavelengths, you determine how much energy is carried by each wavelength, then you find where its maximum is, so this is what's measured, and then you can find out what the surface temperature of the star is. So a very hot star, a large surface temperature, corresponds to short wavelength, and hence very hot stars appear bluish, while cool stars, low temperature, giving a large value of lambda max, they appear to be reddish. There is a constellation, Orion, the hunter in Greek mythology. Orion was an excellent hunter who was very boastful, but then one day he had a fight with the Scorpio, and after some time, Scorpio managed to bite, according to the legend, the hunter, and he died. And the god Zeus decided to put them on the opposite sides of the sky so that they could never be close to each other, they never run into each other again. So basically, whenever you can see, when Orion appears in the eastern horizon, then Scorpius is not visible. It already has gone down the western horizon, right? That's a nice story that explains, doesn't explain, it just sort of tries to connect the fact that these two constellations are seen kind of opposite to each other. Well, this stick figure is just, of course, there's nothing like this in the sky. It's connected by hand to guide the eye. There are two stars in the constellation of Orion. There is this one, Betelgeuse, in the shoulder of Orion. And it is a cool star, and we'll say more about it in the next hour. But you can see that it appears as reddish. On the other side, the one which is at the knee of Orion, Rigel or Rigel, it's very hot, and therefore it appears to be bluish. Now, to see the color of the star, because the stars, because of their distance, they always appear to be point-like, even when viewed through the best of the telescopes. To see the color of the star, it's best to actually make a photograph out of focus, so that then individual stars appear as little blobs. Okay? So that artificially, by making the photograph out of focus, you increase the size of the image of the star. And then you can see the color more clearly. And that's done here in the inset. And here is Betelgeuse, and here is Rigel.